Hello, everyone. My name is Adam Alidra. I'm a data science student at Southern Methodist University, and today I'm presenting on understanding word embeddings in multimodal large language models. So for today's agenda, I'd like to start out by first and foremost getting everyone acquainted and understanding neural networks in general, and then specifically looking at the architecture and design for transformer neural networks, which has really enabled generative AI, large language models, and multimodal large language models. From there, we're going to look at the positional encoding process, which lends to better understanding and analyzing vector embeddings. Once we have an understanding around all these other concepts, we'll tie it all together through a summary understanding of multimodal vector embeddings. So a neural network is a computational learning system that uses a network of functions to understand and translate a data input of one form into a desired output, typically in another form. And this whole notion around neural networks, it really stems from and is inspired by human biology and specifically how neurons work within the brain function. Obviously, neural networks work a little bit differently by instead learning from processing a large corpus of labeled examples, essentially data with answers, a form of supervised learning that is supplied during the initial during the training phase of the model build and paired with an answer key to learn what characteristics of the input are needed to construct the appropriate output. And once there's an adequate number of examples that have been processed, the neural network can then begin to process new and unrealized inputs while successfully returning accurate results. So the idea is the more examples and the variety of those examples that are inputted into the program, the more accurate the results typically become because the program learns based off of that empirical data. So a good way to illustrate all of this and really make it real is by taking a look at the image on the top right, where you have a cat and you have all of these layers between the image of the cat and the word cat. And for humans, it's a lot easier to be able to identify a cat once you see that particular object or animal in this case. But for machine learning, you have to approach the problem a little bit differently. So the way that it works is neural networks essentially take a generalized approach to understanding the content in an image using several layers of functions to first and foremost decompose the image into data points and, in essence, information that a computer can actually utilize. And then the neural network can then start to identify trends that exist across the many examples that have been inputted and fed into the process, ultimately being able to classify images based off of those common denominators, right, or those similarities. And so after processing many training examples of cat images, the algorithm now has a model of what elements and the respective relationships look like in that particular image to consider when looking at a new image, whether it actually correlates and resembles the image that it was trained on. So in this case, is it in fact a cat or is it not? And then it's just a matter of using some simple statistics to make that determination. Now, in the example, or rather the image on the bottom, this is just a very simple illustration of how a neural network pattern looks, right, and how it works. The reality is neural networks tend to be a lot more complicated, and we're going to start looking at that here in the upcoming content. So now that we have a general understanding of neural networks, I want to specifically home in on transformers and also discuss some of the earlier models that have really evolved to or really position transformers based off of their need. So transformers were developed to solve the problem of sequence transduction or neural network translation. And a few common use cases include speech recognition, text-to-speech transformation. When we're thinking about multimodal large language models, even the ability to use, for example, natural language to produce images. So before transformers, there were and continues to be recurrent neural networks or RNNs, which can be thought of as multiple copies of the same network and have loops in them, allowing data to persist through that continuum between input and output. So what you're looking at here is that in the image above, you have A processes some input X underscore T and outputs H underscore T. Now, an important part of this and a distinction from, for example, transformers is each word is processed separately, and the resulting sentence is generated by passing a hidden state to the decoding stage, which generates the output. Now, the shortcomings of RNN start when we're dealing with complex natural language prompts, right? That initial input, where the gap between the relevant information and the point where it is needed become very large. A function of a long sequence or chain, very much like you can see through the through the illustration above, right? It's a very kind of linear process in that particular model. So along the way, there was also kind of an iteration through long short-term memory, which aimed to solve for some of this, but we still ultimately landed into some of the same issues with probability exponentially decreasing as the distance between points also increased. So what came about was this yet another model called convolutional networks, or CNNs, which we continue to see, especially from an image analysis perspective, which got us a little closer to solving for sequence transduction through trivializing to parallelize, very much like you can see in the image there, through the varying layers, by also exploiting local dependencies, and then shifting away from more of a linear approach to producing an output to more of a logarithmic approach, right? So taking a look at the distance between positions and using essentially exponents, or again, logarithms to be able to make those interpretations and correlations. So we ran into the same sort of problems, figuring out dependencies when translating sentences, which brings us to transformers. So the transformer architecture that you're looking at here is based off, first and foremost, the assumption is that there were 6 encoders chained to 6 decoders. Nothing particularly magical about that. That just tends to be a little bit more of kind of a default. Now, the transformer neural network receives a prompt and converts it into sequences and or rather a sequence of positional encodings. And as part of that, you'll also see that there's a sequence of word vector embeddings. Word vector embeddings are, in essence, a numeric representation of the set of the text that is both dense and highly dimensional, right? And this is what really enables the ability to analyze using linear algebra techniques like cosine similarity to determine the similarity or dissimilarity between two words, especially in respect to the input and the output that's being derived. So the transformer adds both vector types simultaneously versus sequentially, right? So this is a really important distinction from RNNs, where things are happening, that process is happening in a very parallelized manner. And what enables that is these attention mechanisms or self-attention mechanisms, and you see that in the form of what are called multi-head attention mechanisms in this particular workflow. The last point I'll make, which we'll come back to, is through this process of encoding and then having the decoders convert the encodings back into a sequence of probabilities, a different output words. Probabilities can then be converted into another natural language sentence using the softmax function. So we'll take a look at that. So what I want to do now is actually pivot to just a quick whiteboarding example and demonstrate what that looks like. Okay, so what we want to do here is we specifically want to take a look at how the positional encoding layer and transformers work. And so suppose you have an input sentence sequence rather of length L, and require the position of the kth object within the sequence, right? So as you think about words and where they may fit from a sentence perspective to produce the appropriate output, the positional encoding is given by sine and cosine functions of varying frequencies, where P P. All right, K 2I equals 9 K over N 2I over D. And then we have P, K, 2I plus 1 equals cosine. And in the interest of time, I'm just going to put quotation to represent this. It looks exactly the same as the formula above. And so K represents the position of an object in input sentence where K is greater than or equal to 0 and less than else over 2. D is the dimension of output embedding space. P, K, and J represents the position function for mapping a position K in input sequence to index K, J of the positional matrix. And N is a user-defined scalar set to, in this case, 100,000, and then I is used for mapping to column indices where I is greater than or equal to 0 and less than D divided by 2, with single value of I maps to both sine and cosine functions. So now to take all of this abstract linear algebra and actually bring it home with an actual example, let's assume that we have a sequence I am a robot. You have the index of the token represented by K. And so 1, 0, 1, 2, 3. And this matrices right here is the positional encoding matrices where D equals 4 and N equals 0. And so what we have here is I equals 0, I equals 0, I equals 1, and I equals 1. The reason for that, as you can see here, we have in this column right here, we have sines, and then we have cosines on this particular column, and then we get back to sines. So these are both sine examples, and then these are cosine formulas, right? Now, without necessarily going through each one of these, what we do is we essentially produce an output. In this example, this is 0, this equals 1, this equals 0, this is equals 1. And that number right there represents essentially the encoding respect of that particular word in respect to where it fits in the sentence and what it means in terms of as it goes up through that transformer process, which I just described before, and it goes through that process of encoding, decoding, and going through that multi-intention mechanism. So a final point here is so this positional encoding matrix actually would be the same for any 4-letter phrase where N equals 100 and D equals 4. So what I want to do now is let's get back to some content. Okay, so now that we've talked about the positional encoding, I want to just briefly talk about embeddings and calculating self-attention. So this is an example, the scale dot product attention function. Well, you'll notice there are effectively 3 vector types. The first of which is Q, representing vector of queries of dimension dk. K is the vector of keys of dimension dk. So think about like key value pairs. V is a vector of values of dimension dk, in essence, the output, and then dk represents the size of the attention keys. So think about this in the context of like the weight. So Q, K, and V are created by multiplying the embedding by 3 matrices trained during the training process. You'll notice that the embedding up top there is larger than each of the vectors. And this is because the dimensionality of the vectors in this case is 64, whereas the embedding encoder input output vectors have a dimensionality of 512, enabling this multi-head attention mechanism that I alluded to previously. So multiplying x1 by the WQ weight matrix produces Q1, the query vector associated with that word. We end up creating a query, a key, and a value projection of each word in the input sentence. So again, the vectors are basically abstractions of the words they represent, which are useful for calculating and thinking about attention. Now, in the second step in calculating self-attention, the idea is to calculate a score. Say we're calculating self-attention for the first word in this example, thinking. We need to score each word of the input sentence against this word, and this score determines how much focus to place on other parts of the input sentence as we encode a word at a certain position. And so it's basically the score is calculated by taking the dot product of the query vector, as you can see there at the bottom, with the key vector of the respective word we're scoring. So for processing the self-attention for the word in position number 1, the first score would be the dot product of Q1 and K1. And the second score would be the dot product of Q1 and Q2, equating to 96. So the third and fourth steps are basically to divide the scores by 8, which is the square root of the dimension of the key vectors used in the paper, 64. 64 square root of that is 8, and this leads to having more stable gradients. And there could be other possible values here, but basically this is the default. And we pass the result through a softmax operation, which I described earlier, and that softmax normalizes the scores so they're all positive and add up to 1, right? So 0.88 plus 0.12 equals 1. And the softmax score determines how much each word will be expressed at that particular position. And clearly the word at this position will have the highest softmax score, but sometimes it's useful to attend to another word that is relevant to the current word. And so the fifth step is to multiply each value vector by a softmax score in preparation to sum them up. And the intuition here is to keep intact the values, the words we want to focus on, and then drown out anything that's irrelevant. Finally, the sixth step is to sum up the weighted value vectors, and this produces the output of the self-attention layer at this position. So the achieved vector is then sent to the feed-forward neural network that we saw in the previous model. Okay, so in reviewing the process of converting words into numbers, as we call them, vectorization and embeddings, this idea here is we aim to reduce dimensionality and provide contextual similarity as a more efficient and expressive representation. A plot of word embeddings in English. And so what you're looking at here is a plot of word embeddings in English and German. And the semantic equivalence of words has been inferred by their context, so similar meanings are co-located. And this is because the relative semantics of words are consistent, whatever the language. So let's again just do another quick whiteboarding exercise here. Okay, so the first thing I want to do is simply illustrate how the attention mechanism works. Attention. Let's say you have the red house. Red house. And we assign some values to that. 0.06, 0.32. And so when we're thinking about, let's say maybe from a translation perspective, let's say we want to go and translate the red house into the form of Spanish, so La Casa Roja. The idea here is to show the attention vector between each word in source and target, which looks something like this, right? So let's say we have La Casa Roja and the red house. So now we're going to have a matrices that essentially represents the correlation between these different values. 26.14, 60, 0.12, 0.80, and then 0.08. And so going back to the image that we just looked at here, right, where you have all of these different words, what we end up doing is we start, we use cosine similarity to determine essentially the similarity or the closeness between two different objects, right, or words. So let's say you have a word one and you have a word two. The closer these two are together, in essence, the closer they are to one, the likelier that there's a similarity between the two words. Okay, so then that brings me to just one other illustration here, and then we'll close out with a final slide here. So this is a positional encoding matrix from scratch, where you in essence have the formula that I illustrated before, right? So pk 2 times 1 equals np dot sine, and then you got cosine right there. And as you can see here, there's a matrices that's developed or set up. And then here is a graphical representation that looks at sine wave for different positions where n equals 10,000. So actually that was 10,000 and d equals 512. And so the idea here is number one, the function's range is between -1 and +1, and the frequency of this waveform is the number of cycles completed in 1 second. And the wavelength is the distance over which the waveform repeats itself. So you'll notice that each position k corresponds to a different sinusoid, encoding a single position into a vector, and a wavelength for a fixed I is given such that a geometric progression occurs varying from 2 pi to 2 pi n. And so basically the scheme for positional encoding has a number of advantages. The sine and cosine functions have values, as I mentioned, between -1 and 1, which keeps the values of the positional encoding matrix in a normalized range. And as the sinusoid for each position is different, you have a unique way of encoding each position, right? So again, that higher dimensionality, that density to be able to be able to determine the pattern and similarities between particular words. And if you have a way of measuring or quantifying the similarity between different positions, hence enabling you to encode the relative positions of words. And so this is a visualization of the positional matrix on Bayer values. So I want to round out here with a final slide to bring this all home. Okay, so what you're looking at here, by the way, is not the exhaustive, is not the exhaustive process in which this particular multimodal large language model was developed. But certainly I want to extract a few, I think, relevant parts, especially as it pertains to this overall conversation or discussion. So the first thing I want to do is just, we've been talking a lot about multimodal large language models. At this point, it might sound just simply like a buzzword. But what's really interesting about large language models, like the one you see here, is it has the ability not only to either to generate a response in the form of visuals, but also being able to take an image that already exists from wherever whatever the foundational model is, right, and whatever the model was trained on. So the idea of multimodal large language models is to both be able to change modalities like text to image, but also generate and or retrieve interleaved information like a response versus an image. And our findings show that it's possible to efficiently map the output embedding space of a frozen text-only large language model to that of a frozen generation model. In this work, Stable Diffusion despite both models using entirely different text encoders. So to achieve strong image generation performance, the folks that developed the study proposed efficient architectural changes to learn the large language model to generation mapping effectively, using again a transformer model conditioned on special learned text tokens. And they did so by minimizing the L2 distance, which I described earlier, between its outputs and the outputs of the text encoder of a text to image generation model. So what you're looking at here is learning to process images through through that equation up top. And so the idea here is they first extract visual embeddings with a pre-trained visual backbone and its weights, in other words, theta and LLM weights, and are basically kept frozen. And then they learn a linear mapping, W representing the essentially the index, which maps into a sequence of k e-dimensional vectors that we use, or that they use as inputs to the large language model. And then similarly, they train the index on image caption pairs by minimizing negative log likelihood loss of the token sequence. And so intuitively, the subjective trains a mapping index that allows to translate images into embedding vectors in a token embedding space of the large language model. And then finally, the image retrieval process is similar in the sense that they learn a linear mapping that maps the first token to a p-dimensional vector, and they also learn a linear mapping that maps the pooled visual output of the image encoder to a p-dimensional space. And so these represent image and text embeddings, and they train the model by minimizing essentially the loss. But the interesting call out here is you can see in the image retrieval similarity, in some ways, it follows a little bit of the pattern that we saw through the positional encoding matrix process. And then finally, I thought a really interesting excerpt here was we use the L image encoder to produce pooled representations of generated images and the corresponding real images and report their cosine similarity. A higher score indicates that a generated image is more similar to the real image. So again, we see this consistency where cosine similarity is used. So thank you so much for your time today, and learn a little bit more about multimodal large language models and how vector embeddings apply to these models. It's been a real pleasure.